The universe is really big. We live in a galaxy, the Milky Way galaxy. There are about 100 billion stars in the Milky Way galaxy. And if you take a camera and you point it at a random part of the sky and you just keep the shutter open, as long as your camera is attached to the Hubble Space Telescope, it will see something like this. Every one of these little blobs is a galaxy roughly the size of our Milky Way, 100 billion stars in each of those blobs. There are approximately 100 billion galaxies in the observable universe. The 100 billion is the only number you need to know. The age of the universe between now and the Big Bang is 100 billion in dog years, which tells you something about our place in the universe. One thing you can do with a picture like this is simply admire it. It's extremely beautiful. I've often wondered what is the evolutionary pressure that made our ancestors in the veldt adapt and evolve to really enjoy pictures of galaxies when they didn't have any. But we would also like to understand it. As a cosmologist, I want to ask, why is the universe like this? One big clue we have is that the universe is changing with time. If you looked at one of these galaxies and measured its velocity, it would be moving away from you. And if you look at a galaxy even further away, it would be moving away faster. So we say the universe is expanding. What that means, of course, is that in the past, things were closer together. In the past, the universe was more dense, and it was also hotter. If you squeeze things together, the temperature goes up. That kind of makes sense to us. The thing that doesn't make sense to us as much is that the universe at early times, near the Big Bang, was also very, very smooth. You might think that that's not a surprise. The air in this room is very smooth. You might say, well, maybe things just smooth themselves out. But the conditions near the Big Bang are very, very different than the conditions of the air in this room. In particular, things were a lot denser. The gravitational pull of things was a lot stronger near the Big Bang. What you have to think about is, we have a universe with 100 billion galaxies, 100 billion stars each. At early times, those 100 billion galaxies were squeezed into a region about this big. Literally, at early times. And you have to imagine doing that squeezing without any imperfections, without any little spots where there were a few more atoms than somewhere else. Because if there had been, they would have collapsed under the gravitational pull into a huge black hole. Keeping the universe very, very smooth at early times is not easy. It's a delicate arrangement. It's a clue that the early universe is not chosen randomly. There was something that made it that way. We would like to know what. So part of our understanding of this was given to us by Ludwig Boltzmann, an Austrian physicist in the 19th century. And Boltzmann's contribution was that he helped us understand entropy. You've heard of entropy. It's the randomness, the disorder, the chaoticness of some system. Boltzmann gave us a formula engraved on his tombstone now that really quantifies what entropy is. And it's basically just saying that entropy is the number of ways we can rearrange the constituents of a system so that you don't notice. So that macroscopically it looks the same. If you have the air in this room, you don't notice each individual atom. A low entropy configuration is one in which there's only a few arrangements that look that way. A high entropy arrangement is one that there are many arrangements that look that way. This is a crucially important insight because it helps us explain the second law of thermodynamics, the law that says that entropy increases in the universe or in some isolated bit of the universe. The reason why entropy increases is simply because there are many more ways to be high entropy than to be low entropy. That's a wonderful insight, but it leaves something out. This insight that entropy increases, by the way, is what's behind what we call the arrow of time, the difference between the past and the future. Every difference that there is between the past and the future is because entropy is increasing. The fact that you can remember the past but not the future. The fact that you are born and then you live and then you die, always in that order, that's because entropy is increasing. Boltzmann explained that if you start with low entropy, it's very natural for it to increase because there's more ways to be high entropy. What he didn't explain was why the entropy was ever low in the first place. The fact that the entropy of the universe was low is a reflection of the fact that the early universe was very, very smooth. We'd like to understand that. that. That's our job as cosmologists. Unfortunately, it's actually not a problem that we've been giving enough attention to. It's not one of the first things people would say if you asked a modern cosmologist, what are the problems we're trying to address? One of the people who did understand that this was a problem was Richard Feynman. 50 years ago, he gave a series of a bunch of different lectures. He gave the popular lectures that became the Character of Physical Law. He gave lectures to Caltech undergrads that became the Feynman Lectures on Physics. He gave lectures to Caltech graduate students that became the Feynman Lectures on Gravitation. In every one of these books, every one of these sets of lectures, he emphasized this puzzle. Why did the early universe have such a small entropy? So he says, I'm not going to do the accent. He says, for some reason, the universe at one time had a very low entropy for its energy content, and since then, the entropy has increased. The arrow of time cannot be completely understood until the mystery of the beginnings of the history of the universe are reduced still further from speculation to understanding. So that's our job. We want to know, this is 50 years ago, surely you're thinking, we figured it out by now. It's not true that we figured it out by now. The reason the problem has gotten worse rather than better is because in 1998 we learned something crucial about the universe that we didn't know before. We learned that it's accelerating. The universe is not only expanding, if you look at that galaxy, it's moving away. If you come back a billion years later and look at it again, it will be moving away faster. Individual galaxies are speeding away from us faster and faster, so we say the universe is accelerating. Unlike the low entropy of the early universe, even though we don't know the answer for this, we at least have a good theory that can explain it if that theory is right, and that's the theory of dark energy. It's just the idea that empty space itself has energy. In every little cubic centimeter of space, whether or not there's stuff, whether or not there's particles, matter, radiation, or whatever, there is still energy even in the space itself. And this energy, according to Einstein, exerts a push on the universe. It is a perpetual impulse that pushes galaxies apart from each other. Because dark energy, unlike matter or radiation, does not dilute away as the universe expands. The amount of energy in each cubic centimeter remains the same even as the universe gets bigger and bigger. This has crucial implications for what the universe is going to do in the future. For one thing, the universe will expand forever. Back when I was your age, we didn't know what the universe was going to do. Some people thought that the universe would recollapse in the future. Einstein was fond of this idea. But if there's dark energy and the dark energy does not go away, the universe is just going to keep expanding forever and ever and ever. 14 billion years in the past, 100 billion dog years, but an infinite number of years into the future. Meanwhile, for all intents and purposes, space looks finite to us. Space may be finite or infinite, but because the universe is accelerating, there are parts of it we cannot see and never will see. There's a finite region of space that we have access to, surrounded by a horizon, so even though time goes on forever, space is limited to us. Finally, empty space has a temperature. In the 1970s, Stephen Hawking told us that a black hole, even though you think it's black, it actually emits radiation when you take into account quantum mechanics. The curvature of space-time around the black hole brings to life the quantum mechanical fluctuation, and the black hole radiates. A precisely similar calculation by Hawking and Gary Gibbons